Okay, students, here we go. Let's start chapter 4 and let's get into motion and forces. Okay, now what causes a motion, or what causes things to move, I should say? I think it's pretty obvious that they use this example here of someone sliding on snow. Now, of course, if it's a flat surface, you're going to need someone to push you. But in the absence of friction, if someone was to give you a push, then you would go on forever, okay? And that really goes in line with Newton's first law of motion, that an object has no force acting on it, or in other words, an object will remain at rest until acted upon by an outside force, okay? Or an object will remain in constant motion until acted on by an outside force. So, I know some of you are thinking, well, now wait a minute. You know, I've pushed, when I was a kid, I used to push my wagon, and if I just give it a good push, it'd quit rolling, even on a flat surface. Well, we're not taking into account air resistance, we're not taking into account friction. Those are those outside forces that we're talking about, okay? All right. But if those were not there, then you give that wagon a push and it'd go on forever, okay? All right. So what is a force? It's a push or a pull. It's that simple. So anytime you push or pull on something, then you are creating or producing a force. And, of course, every force has an agent, something that acts or pushes or pulls. All right, that's pretty simple. Now, what is a force as far as mathematically speaking? We've already talked about this. Force is a vector. So we've covered several things now that are vectors. Velocity is a vector quantity. Forces are vector quantities. Acceleration are vector quantities. Later on we'll get into momentum. Momentum's a vector quantity. Remember what that means. It means it has magnitude and it also has direction, okay? Now, they talk about contact forces. Here we would see that the contact force is the bat between the ball. That's the point at which the contact is made. That is right there. That is the contact force, okay? Then you have long-range forces in which there's no physical contact. For example, gravity is a long-range force. If you jump out of an airplane, you will hit the ground, okay, without a parachute. Now, just like with anything else we've drawn vectors for, velocity, acceleration, the same goes for forces. You always point the air in the direction of the force. You always try to represent the length of the vector as the magnitude, okay? And then, of course, you always need to label it, all right? Now, again, here we see if I was pulling on this box, then the box is the point at which it's going to move, and I'm going to pull it a certain distance. Let's say I pull it that far with a force applied, and I have the net force. I'm creating a net force. If I don't pull on it with a net force, it won't move, okay, because the force of static friction has to be less than the actual applied force, okay? So if I don't pull on it with more than its actual static friction force, it's not going to move. Here we see if you drop the box, the long-range force there is the force of gravity. Okay, so short range, long range. All right, now, okay, so when we look at how to combine forces, it's very simple. It's just the sum of all the vectors involved. So we can write this as net force. We can also say the sum of all forces. We use the capital uppercase Greek letter, I think that's sigma, if I'm not mistaken. And so so we write it that way, and then we say it's equal to F1 plus F2 plus normal force or whatever. And we're going to get into all the different kinds of forces, okay? All right, now, and we always put that little arrow, I'm bad not to put that on there, over the top of it, saying that it is a vector, okay? So they're using an example here of the box and two people pulling on it. Your resultant force, or your net force, notice this person's pulling at an angle, this one's pulling straight down. Well, guess what? Your net force is going to be in between the two, okay? Somewhere in between the two. Now, all depends on which one has the greatest force. Now here's a good little quick check, and we will do some of these, but a lot of them I've deleted out because good grief, y'all. I know you don't want to sit here for an hour and a half and listen to a lecture video, all right? Okay, so if you have, and both of these have equal magnitude, so which one of these would be the correct answer? Well, I'm thinking that it's going to be the third force to balance this. Okay, now remember, we want to balance it, not move. I'm thinking it's going to be that one. Let's see. It most certainly is. It's component C. Vertical. This vector causes the other two to cancel, and it does not move. Okay, and that was the purpose of that. Now let's look at how we catalog forces. There are different types of forces. There's basically four types of forces. You have weight, and what is weight? Weight is the actual, weight is the same thing as a force. We say Newton's second law, we hadn't gotten that, so F is equal to ma. Well, guess what? Weight is equal to mg, okay, the mass times the object's, the mass of the object times acceleration of gravity. And so that's how we define the weight, and of course the units for weight, okay, are what? Well, that's going to be the Newton. Well, it's a kilogram meter per second squared, and that is equal to a Newton, okay, capital N. And that's how we write forces. The unit for forces is the Newton. It's a capital N. And it is defined as the amount of force, the amount of acceleration to cause a 1 kilogram object to accelerate with, the amount of force required to cause a 1 kilogram object accelerate at 1 meter per second squared, okay? All right, so that's how we define Newton. So weight, the unit for weight is newtons. It's not pounds, okay? That's the English unit, okay? We have spring forces, okay? And again, it's a force, and notice how we write it. FSP, okay, or just FS, okay? And spring forces are actually what we get into a little later when we talk about Hooke's law, restoring force. They have what are called restoring forces, okay? And that is actually a type of potential energy. There's such things called spring potential energy. And we'll get into that later. All right, so we have tensional force, okay? And again, the unit is newtons, but here we see tension is being put on the sled in this direction, okay? Okay, and of course the direction of the tension force is always the direction of the string or rope. They have to be, okay? Then you have what's called a normal force. Now, normal force is a force that is perpendicular to the surface that an object is resting on or an object is moving on, okay? It's always perpendicular. See that right there? That is a right angle. It's always perpendicular to the surface, okay? They didn't tell you that. Well, yeah, they did. You did. All right, it's always perpendicular to the surface, all right, the direction that force is. So it's very, very important to know that and remember that, because we will be looking at normal forces, and I'm going to get a little ahead of myself. I always like to write normal force this way, F capital N, or we could write it Fn. Now, your textbook uses lowercase n. That's the same unit for moles, even though we're not in chemistry still. But it's actually equal to the mass times the gravity of the object, okay? That's actually how you find the normal force. And get a little ahead of myself, okay? Now, here we see if a person's on a skiing on a slope, the normal force is still perpendicular to the surface. But now, one thing that's going to happen is that the normal force is going to be affected by the angle of the slope, okay? And so it's not going to be the same as it would be if the person was on a flat surface. The incline causes the normal force to be less because they're on an incline, okay? All right, okay. All right, because the cosine of any angle above 0 is less than 1, okay? And so you're going to, where you're going to get your greatest force on a flat surface, greatest normal force, okay? And then we have frictional forces. We have two kinds of friction, and these are exerted on a surface, okay? And they're always parallel. Frictional forces are always parallel to the surface. You have kinetic friction, which is the friction that opposes motion. In other words, an object that is moving. For example, when we're walking across the floor, there is kinetic friction in the opposite direction that we're moving with the bottom of our shoe and the floor. It's called kinetic friction, okay? And it's always in the opposite direction of the motion, all right? Static friction's the same thing, except here it's a little bit different. Static friction prevents motion. Well, what would be a good example of static friction? Well, okay, a book resting on the table, it's not moving. A poster that has been taped to a wall. Okay, the tape, the adhesive part of the tape has enough friction within it, within the bonds. Let me correct myself, not friction, but the strength of the chemical bonds in the tape, in the adhesive in the tape, is strong enough to cause it to stay there. That's how they make these really good adhesives. It's actually bond chemistry, and bonds have forces, and so it's actually physical chemistry, okay? And you're actually looking at the physics of the chemistry there, okay? So static friction, what stops me from, if I'm walking and I want to stand, I've got to stand firm somewhere. Let's say I'm on a roof, and I don't want to slide, okay? I don't want to move. I don't want to stay there and hammer my decking down, okay? I'm on a real steep roof. Well, you want to have a shoe that has a really good static friction, one that'll really make you stick, okay? Static friction's like the sticky friction, okay? And they say stuck there. It's kind of like a sticky friction, okay? It keeps you from moving, all right? So here we see, of course, anytime an object is moving, friction is always, and I mean always, going to be in the opposite direction that you're trying to move it, all right? You're trying to pull this box or crate or whatever, and you're pulling and pulling and pulling. Well, guess what? You've got static friction in the opposite direction. Here the little boy is on his sled, and the kinetic friction, he's moving, but there's kinetic friction in the opposite direction. And by the way, when we look at kinetic friction and static friction here a little bit, we'll get to coefficients. The coefficient of kinetic friction will always be lower than the coefficient of static friction, okay? It'll always be lower. How else would you move if it wasn't lower? I mean, come on, think about it. And we'll get to that here in a little bit, all right? Now, then, of course, you have drag, and drag is a frictional force that resists motion or an object moving through the air, okay, whether it's on the ground or falling from a tree or an airplane or whatever, okay? You have drag. Why does the space shuttle, well, boy, I'm telling my age. I don't even use that thing anymore. But, if you remember anything about the space shuttle, if you've ever heard anything about it, they have those heat tiles on the bottom of it. They come in bottom down. They don't come in nose first. They would burn up in the atmosphere. They come in with the bottom, parallel to the atmosphere, okay? Because what happens is that, as you enter the Earth's atmosphere, you're moving at a speed of about 18,500 miles an hour. You're falling through the atmosphere, and so guess what? You have a tremendous amount of drag, and it causes it to heat up. Okay. Then, of course, there's thrust. We talk about the space shuttle. That thing produced 7.5 million pounds of thrust. The SRBs were about, I think, 1.5 million each, and the main shuttle engines were like 3.5 million, and the total thrust on that shuttle when it took off was 7.5 million pounds of thrust. Are you kidding me? Okay. They said if you could keep it hooked to the pad, it would literally pull the pad that it launched from out of the ground. That is amazing. Okay. So you have thrust. Of course, thrust, we're going to get into Newton's third law here in a little bit. The rocket moves this way, but guess what? The thrust is actually in the opposite direction. That actually goes in along with Newton's third law, and we'll get to that in a little bit, okay? And then, of course, we have electric and magnetic forces. These, surprisingly or not, people don't realize this, that they are much, much stronger than gravitational force. And thank God they are. Thank God gravitational force is not as strong as electromagnetic forces, because we couldn't live on the Earth, okay? And we'll talk about that later, all right? Now, we've got a ball rolling down an incline off the horizontal ramp and ignoring air resistance. What force or forces act on the ball as it moves through the air just after leaving the horizontal ramp? Well, which one do you think it is? The force direction Let's see, the horizontal force that maintains those, the weight of the ball acting vertically down, the weight of the ball in horizontal, the weight of the ball and the force and direction of motion. Which one do you think it is? Well, of course, it's the weight of the ball. That's it. If you remember from previous chapter, I think it was chapter 3, we was talking about projectile motion. The only force acting on it once it leaves is that one right there, the weight, gravity, mg, okay? That's it. Once it leaves the ramp, that's all that's acting on it, okay? And you should remember that from chapter 3. We've got a steel beam hanging from cables as a crane lifts the beam. What forces act on the beam? Well, of course, we got gravity. We got gravity and tension, gravity and the force of motion, gravity and tension and force of motion. Well, let's see, it's hanging from cables and it's being lifted. Well, let's see, there's tension in the cables, there's gravity pulling it down. I would say that it would be both of those, and it most certainly is. Okay, so think about that. All right, let's look at identifying forces. Now, identifying forces are very important. When we are doing what we call free body diagrams, you need to always look at all the objects that are of interest, draw a picture of the situation, and I preach this and preach this and preach this and preach this to my kids in Cal-based physics. I had a cousin that was an engineer, taught at Florida State, had an engineering firm, taught many years at Florida State, and he told me, he said, whatever you do, you make sure those kids draw those diagrams and label them. He said, because you can explain any engineering problem with a free body diagram. That's what he told me. He said that's very important, and I believe him because he's been very successful, very smart. Okay, so you got to draw the picture. You draw, and it doesn't have to be beautiful. You don't have to be an artist. Just draw it. Now, draw a closed curve around the object. Okay, you can do that. I typically don't, but you can. Locate every point on the boundary of the curve where the objects and other objects touch the object of interest. That's always important. Label all your forces and name and label all the long-range forces acting on it. Very important. Now, here again, there are common forces. Now, I kept this slide. This is good because this helps you to understand when you see it, well, what the heck is that? All right, general forces in, let's say, like an applied force, we would just say F, like I'm pushing on a box. Well, I would label that F. Then you have weight. Well, you label that as W, lowercase w. Spring force, you can say FSP or FS. That's typically what I do. Tension is T. Normal force, now again, lowercase n, this is how I like to write it, F of n or F. I usually use a capital N, normal force, okay? Static friction is always written with that script, lower script F, S, and the same thing kinetic with lowercase k. Drag is capital D, and then F thrust is F thrust, okay? So it's good to, familiarize yourself with these symbols. That'll help you to understand what's going on. Now, here they give you a conceptual problem. Bungee jumper has leapt off a bridge and is nearing the bottom of the fall. What forces are being exerted on the bungee jumper? Well, notice, and again, this is a student sketch. They circle it. They draw a cable. They have the student hanging from the bungee cord. There's his legs, his feet, and his body, and his arms. Now, I do a lot of stick figure drawings too, and his head. Okay, you have the tensional force in this direction. I would have drawn that. I would have drawn the arrow there. And then we have what else? Well, we've got weight, don't we? We've got gravity pulling him down that way, don't we? The weight of the object. Actually, it's gravity, gravitational force, or weight, okay? All right, now, same thing. Here's another drawing. You've got your normal force, your kinetic frictional force, your tensional force, and you would actually need to draw the angles in there, and we'll get into that a little bit later, okay? All right, now, what do forces do? Here we see, of course, if you stretch a rubber band, a standard length rubber band, and it's just one rubber band, it's F of 1, right? It takes whatever the force is for you to stretch it, say 5 inches, okay? But what if you double the number of rubber bands? You got the same type, same style, same size, everything, and you put 2 of the same identical rubber bands on your finger. Well, okay, come on. If it took F to stretch 1 5 inches, it's going to take 2F to stretch 2 5 inches, okay? All right, that's common sense, isn't it? Sure it is, okay? So same thing here if you're pulling. Now look, if you want to pull with a constant, notice it says here, in order to keep the force constant, you must move your hand to the right to keep the length of the rubber band to the right, just the right way to keep the length of the rubber band, and thus the force constant. Okay, again, they're using rubber bands. It could be a rope, but if you want to keep a constant force, guess what you got to do? You've got to give it a constant acceleration, okay? Constant acceleration, all right? So what do forces do? Well, of course, again, we've already talked about this. An object pulled with a constant force moves, you better remember this, with constant acceleration. I just said that. And another thing, acceleration is always directly proportional to the force. Okay? And its acceleration is inversely proportional to an object's mass. So, let's look at this. We cart is pulled to the right with a constant steady force. How will its acceleration graph look? Well, okay, notice it says with a constant steady force. All right, so we got a constant force, F, and you might want to say constant right here, okay? Well, guess what? It should look like that right there, shouldn't it? All right, well, let's see if we're right. We are right. Absolutely, you got to have a constant acceleration, okay? Well, why is that? And they're kind of getting the cart in front of the horse. Again, forces move in the direction of the applied, objects move in the direction of the applied force. And the force and the acceleration are directly proportional to each other. So, Newton's second law says what? That an object will accelerate in the direction of the applied force. That is Newton's second law, okay? So we can write it this way. Notice how acceleration and force is directly proportional, and it's inversely proportional to the force. So we could write this. We could say force is proportional to A and 1 over and inversely proportional to mass. Okay? All right, so you could, and again, we write that little proportional sign there, okay? All right, does that make sense? I don't want to confuse you. Let me do it this way. All right, so we got force is directly proportional to acceleration, and force is inversely proportional to the object's mass, right? All right. Well, actually, they're saying acceleration is. Sorry, I wrote that wrong. Okay. My bad. Well, same. It's the same principle. And then the acceleration is what? There we go. All right, inversely proportional to the mass, okay? So how do we write Newton's second law? You can write it this way, but you can also write it this way. This is how it's typically written, F is equal to ma, okay? F is equal to ma. And that's how we write Newton's second law. So there's your another formula. Add to your formula card. Hint, hint, hint. Add it to your formula card. So there we see the equation again, and here they wrote it in standard form. And you do need to write that on your formula card along with those others I told you to write. We've got a constant force causing an object to accelerate at 4 meters per second squared. What is the acceleration of an object with twice the mass? Okay. So we have a constant force. So we got A is equal to F over m, okay, and it is equal to 4 meters per second squared, isn't it? Okay, well, what happens to the acceleration? We go A is equal to, let's see, and it's a constant force, so this is constant, okay? All right, pretend that says constant. What is the acceleration of an object with twice the mass? Okay, well, all right, we've got the force is constant. Okay, now we got 2m. Well, it's 1/2, isn't it? So it's actually 1/2 what it originally was, so it should be what? Which would be, what was 1/2 the original? What was the original? 4. 1/2 of that would be 2, right? And it's right. Okay, there you go. That's how you do it. Real easy, all right? All right, notice if we have a basketball, acceleration of a wind-blown basketball. If you drop a basketball and wind's blowing to the basketball is released from rest, the stiff breeze is directed to the right. So the breeze is going that way. Okay, wind. All right, which way is the ball going to move? Okay, well, naturally, y'all, you know that the wind is going to push the ball over this way. So the actual force is going to be in that direction. And so also is the acceleration vector, because remember, acceleration and force are directly proportional to each other, and here they explain it. If you want to read all that, fine, but I just told you why, okay? Free body diagrams. Very important you understand how to draw these free body diagrams. I preach this and preach this. Of course, you always need to identify the forces involved, draw a coordinate system. That's like this right here. Draw a coordinate system. Represent the object as a dot. That's the best way to do it. At the origin of the coordinate axis, like, in other words, put it right there, okay? And then draw vectors representing all the forces and draw and label the net force vector, okay? Very important, okay? You're in an elevator lifted by a cable. It's moving upward and slowing. Which is the correct free body diagram? Okay, so you're moving up. So we got an elevator, and it's going up, but it is slowing. All right? Well, we know that what? mg, weight, that's weight, right? There's another formula to write on your formula card. Weight is equal to mg, okay? All right. All right. So which one of these do you think? Well, I think it's that one right there. What do y'all say? And it most certainly is, okay? Well, why is the tension shorter than the weight? Well, because it's slowing. It's moving up. It's slowing, so therefore the tension is not as great, all right? A ball has been tossed straight up. Which is the correct free body diagram just after the ball has left the hand? Ignore air resistance. So we're down here on the ground, okay? All right. Now there's your coordinate system, and I'm drawing the little boy. I'm not drawing the dot, okay? I know it said draw the dot, but I like to draw the person. All right, so he's got a ball, and he just releases it, okay? And it's moving up, okay? That means it's moving up, all right? So it's going straight up, okay? Which one's the correct diagram? All right. It come out of my hand. Just as it comes out of my hand, the only force acting on it is what? Well, I think it's going to be that one right there. You say, well, wait a minute, it's going up. There's a force pushing it up. No, there is not. Okay? No, there is not. I gave it an initial velocity just as it come out of my hand. Okay? I gave it an initial velocity. You say, well, how do you know there's not a force pushing it up? Well, let me ask you something. Have you ever thrown something straight up? Yes. What happens to it eventually as it's going up? Well, it goes up, and then does what? Stops, doesn't it? Well, if there was a force in the upward direction, it would not stop. Okay? So what makes it stop? Da, 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 da. Okay? So let's see if we're right. And we are right. The only thing acting on it is gravity, okay? Now let's look quickly at, Newton's third law. And Newton's third law is often referred as the action-reaction law. If you've ever thought about when you push on a wall, here they're using taking a hammer, driving a nail. This is a really good demonstration. You're applying a force in this direction on the nail, but guess what? The nail is applying equal but opposite on the hammerhead, okay? Same thing when you kick a soccer ball, if you hit a baseball, what would be another thing? Shooting a rifle, bullet goes out the barrel, and the bullet, the bullet goes out the barrel pushes back on the bullet, so same principle. Okay, now, so we call this the interaction, we have what's called interaction forces, or the action-reaction pair, and always remember that forces act in pairs, okay? It's very, very important. Okay? You can't have a single force. They always act in pairs. Okay? Alright, so we call this the action-reaction, or if you want to get technical, you apply a force to an object, and the object applies a force equal but opposite direction. And how do we write that formula? F of 1 on 2 is equal to negative F of 2 on 1. Okay? They're equal, but you say, well, why don't we write it that way? Well, because look, it's in the opposite direction. That negative tells me it's in the opposite direction. I'm getting a little ahead of myself. Again, every action-reaction forces, they act in pairs. I've already said that. Here we see person walking across the surface. There's a frictional force in the opposite direction as a person walking. Here's a good example of Newton's third law, moving upward. You got the rocket going up, and you got the thrust going out, okay? All right. We've got 10-year-old Sarah stands on a skateboard. Her older brother starts pushing her backwards, and she starts speeding up. The force of Jack on Sarah is what? It's greater? Or less than? Oh, heck no. It's equal, y'all. That was a trick question, wasn't it? Yeah. Newton's third law. It's equal. And that's the point of contact now, okay? Mosquito runs head-on into a truck. Splat. Which is true during the collision? All right. Well, what do you think? Everybody say C? Yes, C is correct, okay? C is correct. So here we see Newton's third law, and I'm going to stop right here. And we didn't actually get in a formula for it, but, well, yeah, we did. I wrote it. Newton's, okay, third law. Newton's third law says what? That's his first law. Let me back up. Let me back up. There it is. Oh, now. Okay. So Newton's third law f of 1 on 2 is equal to negative f of 2 on 1. Okay? This would be 1, this, or no. No. Oh, I do not like this new form of PowerPoint. This would be 1, this would be 2. Okay? Alright. Everybody follow me? So you notice the arrows in opposite directions, okay? Alright, I hope this helps.